All right, so let's now take a deeper dive at XPS Spectra. So what it looks like, what information we get, and some of the features that we tend to see. So we're going to take a deep dive on the spectra. So um, we've seen that in the last examples that we can identify the peak in AES, but also in XPS fairly straightforwardly. But XPS is a little more complicated because you already noticed the one peak here. So if you had trouble identifying that, that's because it was an Auger peak, right? And so that makes XPS a little bit more complicated than AES, because with AES we don't have those transitions. So that's one complication that we have. However, there's a way that we can identify these. So if we not sure if it's an Auger peak or not, we can actually change the X-ray source, right? So we had these X-ray guns that had the option to switch, right? So a switch in the X-ray source will cause a shift in the Auger peak that we have, because we're looking at apparent binding energy, and that changes with energy. And so, if we're looking at the energies for our different sources here, there's a difference of 233 electron volts. And so we would expect that the shift would be based on that. So that's one kind of complicated way that we could, basically switch the gun and be able to determine if that's an Auger transition or not. So there are ways to do to determine what we have. All right. So we've seen this a few times now, but let's kind of go over what I call the survey scan, and that's the broad scan of basically looking at a wide range of binding energy values. So we plot it versus binding energy. Sometimes you'll see kinetic energy plotted in the opposite way or on the top of the graph. And then it's always plotted against intensity. So this is either electron counts or intensity. And so that's the way that we're going to see it. And we have the core electrons, such as 3s, 3p, 3d, all the peaks that we've been talking about. We can also see Auger electrons. They tend to be at the higher binding energies. All right, and then at the lower binding energies down here, we can also see valence level electrons. We don't always see these. A lot of times we just see background, but this is also possible to get valence level electrons. And this can be useful for studying the electronic structure of atoms. All right, so the interesting thing here, and the one thing you might notice with these spectra, is that the XPS background is actually the step-like feature. So we kind of see that it's relatively flat here, we have a peak, and then the background steps up. So this is because we have inelastic scattering of photoelectrons in the solid. So that's kind of the cause of this. And we also have background at the low binding energies. We can have that from non-monochromatic radiation. So if there's an issue with that not being one wavelength, then that can also be the issue there. So we have kind of a different background than maybe we're used to. So when you're kind of doing the fitting process and trying to get peak identification and peak areas and things like that, the background that we use is not going to be a standard kind of linear background or something that you may be used to in other applications. It's actually known as a Shirley-type background, and this models that step from the inelastic scattering. And so this is an example from a common software called CASA SPS, where it's basically showing this step function. And so that's something that, if you're trying to use generic fitting software at home to fit XPS data, then that's something you have to consider. You can't just use the standard fitting software. So you got to use Shirley-type. All right. So some other things that we can see in XPS spectra. We can see what we determine, what we kind of think of as extra peaks. And so these extra peaks, in this case, what we see here, are from interaction of the photoelectrons and the valence electrons in the atom. So in this case, we're looking at copper, and we have the copper 2, and so we have the 3 halves and the 1 half. But we also see these extra peaks. We really only expect to see 2 peaks, but in this copper oxide, we actually see these shake up satellite peaks. And again, that's when these photoelectrons that we've produced excite or shake up a valence electron to a higher energy state. And so that's something we can often see, and copper is very common. And so it's not necessarily a bad thing. It can also help us identify copper or the type of copper that we have. So that's just one thing in addition that we tend to see as these shake up satellite peaks. Another thing that we can sometimes see, this is an example of aluminum, again, aluminum 2P, is we can see what's known as Plasmon loss. So this is similar to that satellite peak that we saw in the previous slide, but in this case, it's from excitation of the conduction electrons. So not the valence, but the conduction electrons. And so we have kinetic energy loss. Therefore, that means that if there's loss in kinetic energy, that means a higher binding energy. And so that's, again, here at the higher values from this 72 or so, this is a higher value there because those photoelectrons are basically causing vibration of the conduction electrons. So that's another thing that can happen. And again, these aren't always bad things. They can often help us identify what a material is. But we do have to consider it that there are these other kinds of peaks that we may not see in the basic charts like you saw in the handout. All right, so XPS, like a lot of things, a lot of spectrometers, relies on calibration. We need to have some type of standard. And in a lot of these spectra that we've seen, we notice carbon. And it's around 285 electron volts. And we see this in most specimens, even if carbon isn't in our sample, because carbon, that carbon-carbon bond of graphitic carbon, is in hydrocarbons. It's in a lot of impurities. It's on the surface of a lot of things. So that's obviously not always the best thing, but it means that carbon's always there, and it's got a very defined peak. And so we often use carbon, either whether it's there on purpose or not, as a way to calibrate our spectra to the spectrometer conditions and what the sample surface is like. And so, we can see something, a peak like this that's the carbon bond, which should be at 284.5. And we can, if our value is something different, we can basically shift that to accommodate for the conditions of our XPS and also the sample condition. And so you can kind of think of this in the terminology of previous methods as the internal standard method, right? Because we're adding in a standard, carbon in this case, to allow us to calibrate the machine. And so we're basically shifting the spectra based on that. All right. So one thing that I'm going to bring up here is can be another difficulty of XPS identification, and it's that peaks can shift, and they can shift because of their chemical environment. So I just mentioned that carbon peak. That's the carbon 1s peak, and it should be at around 284.5. However, when we talk about the carbon 1s range, we often talk about a range of over 12 electron volts, because carbon can change depending on the local chemical environment of carbon. And so that's what we see here. We see 4 peaks, and it's not 4 different elements. This is all carbon. It's just the carbon in 4 different local environments. So this is important to keep in mind, is that, again, we have tables for carbon, 1s, oxygen, all these, but it can shift due to the chemical environment. And so this can make it difficult, or one extra thing we have to think about. But it can shift. So the example here is that carbon is actually a part of this polymer PVTFA. And so in polymers, we know that there's different bonds of carbon, the carbon backbone, but then there's also carbon with the side groups and so forth. And so that's what we're seeing here, is those 4 different environments of carbon in this polymer.